Okay, so we will continue to prove proposition 3.5.1. So let me state this proposition again. All right, so for any event f in the sigma algebra f, the conditional probability, okay, is a function from the sigma algebra f to the set of all real numbers which satisfy the three axioms of a probability function. Okay. All right. And there are two cases to discuss. So case number one, that if the probability of the probability that the event f occurs is equal to 0. Okay, so this is the first case. And as we have demonstrated that in this case, then we have defined that the conditional probability of event E given f is just the unconditional probability of the event E. Okay, for all event in the sigma algebra f. All right, so that the proposition follows immediately. Okay, because the P is a probability function, right? Okay, so of course, satisfy the three axioms of a probability function. All right, so now we consider case number 2. That the probability of event f is positive. Okay? In this case, the conditional probability of an event E given event f is just the ratio of the probability of the joint event E and f divided by the probability of f. Okay. All right, so it is clear that P of E given f is greater than or equal to 0 for all, and the conditional probability, okay, of the total event given event f, okay, is this ratio, but the intersection of the total event with event f is equal to the event f. So that from here, this is 1. Okay, so that this function, all right, satisfies xm number 1 and the 2 of a probability function. Okay, because this one tells us that that this function is non-negative, and here, okay, this expression tells us that this function is normalized. Okay, all right. So now we have to check the countable additivity of this function. Okay. Now, okay, now for a sequence E1, E2, of mutually disjoint events in F. Okay, so for such a sequence of mutually disjoint event in F, then E1 intersect F, E2 intersect F, etc. Right, is also okay. So R, all right, are also mutually disjoint. Okay, right. So these are mutually disjoint, and then okay, and then we consider the conditional probability of the union of E sub n given the event f. Okay, the event f here, and by definition, we know this is the ratio of the joint probability divided by the probability of f. Okay, and so by the distributive law of intersection to the union, so this is becomes to okay. All right, so now the numerator is the probability of union of events, all right? And as we see that this is sequence, all right, is a sequence of mutually disjoint events, all right? So this is again a disjoint union, okay? So let me write that here. So this is the disjoint union, and again, this is a disjoint union. Right. So we apply countable additivity of the probability function P here, right? So this is the summation of probability En intersect F. Okay. Divided by PF. Okay. All right. And so this is the summation of this ratio here. But this ratio is just the conditional probability of En given F. Okay. So you can see that that for such a disjoint union of events, okay, its conditional probability given F is equal to the summation of the conditional probability of individual event En given F. Right, so that P dot F satisfy. So that satisfy axiom number 3 of a probability function. Okay, so we've done. Okay, so we have shown that this function, okay, this function is a probability function. All right, so from the previous proposition, okay, so from the previous proposition, we have so corresponding to an event F in the sigma algebra, there X a probability function P, okay, on the sigma algebra. Okay. And so for convenience, okay, we denote the conditional probability of an event E given event F, right, by this notation. Okay, so this is a probability function. And the subscript F indicates that it's actually a condition on the event F. Okay. For OO, okay, so all properties about a probability function, especially in section 2.4, right? We list quite a few general properties of a probability function, okay, as well as the continuity property in section 2.6. All right, all these properties can be applied to this probability function, okay, P sub f. Okay. So for example, from proposition 2.4.3, we have that P sub f E1 union E2, okay, is equal to P sub f E1 plus P sub f E2 minus P sub f E1 intersect E2, right? And if you return back to the original formulation here, this is corresponding to the conditional probability of the union of two events given event f, okay, is equal to the conditional probability of event E1 given f plus the conditional probability of event E2 given f minus the conditional probability of event E1 intersect E2 given f. Okay. Okay. So they are equivalent, but using different notations. Okay. And of course, as we have shown in section 2.4, we have inclusion-exclusion principle, okay, for a probability function. So again, we have the inclusion-exclusion principle for this probability function P sub f, okay, P sub f. So similarly, we can define conditional probability, right, relative to this probability function, right? So for P sub f of g, right, which is g given f, so for the case that P sub f of g is positive, all right, so we define the conditional probability P sub f E given g by this formula. Okay, so it's the ratio of the conditional probability of this joint event given f divided by the conditional probability of event g given f here. Okay, all right. So in this case that this is just regarded as a probability function. Okay. And for the case that the P sub f of g, which is this one, when this is equal to 0, then we define, okay, that Pf E given g defined to be Pf given E. Okay. Okay. All right. So now we have several additional proposition. So the first is 3.5.8. For any events, okay, E, F, G, we have P sub F E intersect G is equal to P sub F of G and P sub F of E given G. All right, and this one is basically from so this is actually the multiplication formula, right? The multiplication formula for okay, so that this is the multiplication formula, all right, for P sub F. Okay. And in general, for any events E1, E2, up to En, and F, okay? We have, all right, P sub F of E1 intersect E2 intersect intersect En. Then this is P sub F of E1 times P sub F of E2 given E1 times P sub F of E3 given E1 intersect E2, okay? Up to P sub F En given E1 intersect E2 intersect up to minus 1. Okay, so this proposition is a direct application of the multiplication formula for any probability function. Okay, because we have shown in proposition 3.5.1 that P sub F is a probability function. So of course, it has the multiplication formula. Okay, we developed in section, I think in section 3.2. Yeah. Okay. So we call multiplication rule. Okay. So I'm sorry. Maybe I changed the name. Okay. So this is the multiplication rule. Okay. And this formula here is just a special case when we have two events here. But in general, if we have n events, okay, so the joint event, okay, under this conditional probability function, okay, P sub F here, we have the same formula here. Okay, we have the same formula here. Now, All right, and so so in here, okay, we define conditional probability, right, for this probability function. But as we establish P sub f, we know actually P sub f is a conditional probability of an event given the event f, right? So that implicitly we have already a conditional probability here. All right, and so the next proposition, establish a connection, okay, among these concepts of conditional probabilities. B. All right. Now, if the joint probability of FMG is positive, then so if this is true, okay, if this is true, then the conditional probability of event E given event G under the probability function P sub f. Okay. This function, this conditional probability is actually equal to the conditional probability of event E given the joint event G and F. Okay, given the joint event G and F here. And so from here, we can write down. Okay. So actually, we can use another probability function. Here, the condition event is G intersect F here. Okay. And so now F and G is exchangeable. Okay. So now we can use P sub G. All right. You have to know P sub F, P sub G intersect F. These three probability functions may be different from each other. Okay? They may be different from each other. Okay, and so that you can see that the concept of conditioning, okay, can be done in two layers. This is kind of the two-layer conditioning, right? So given F, right, and then given G, right, and this becomes to conditional probability of event E given G and given F. Okay, so it's two layer. And this two-layer conditioning actually is equal to the one layer condition, that is the conditional probability of event E given the joint event of G and F here. Okay. And the two-layer conditioning, all right, this two-layer conditioning is equal to this one. So you can see that you can exchange the role of F and G. Okay. So in here, the first conditioning is F and then G, and here the first condition is G and then F. Okay. So they are symmetric. Okay. Right. So this is a very good proposition to illustrate that they are they are harmonic phenomena between this concept of conditioning. Okay, so let's see the proof. And the important thing is that we have to assume that the joint probability of event F and G is positive. Okay. Now, so the proof is that since the joint probability of F and G is positive, okay, and we know that P of F and P of G given F. So we use the multiplication rule. All right. So this is the joint probability. So the joint probability is the product of these two, right? And also it can be expressed in this way. Okay, it's in this way. Now, because this is positive, so any factor, right, must be positive. So we have, okay, so we have PF, all right, so the probability of event F is positive, P of G is positive, okay, and right, so that P sub F of G, okay, so by our definition, we know this is P of G given F. So this is probability G intersects F, PF. Okay, must be positive. And similarly, PG of F also positive. Okay? Right. So positivity of this joint probability implies positivities of this probability. Probability of F, probability of G is positive, and the conditional probability of G given F is positive. Conditional probability of F given G is also positive. Okay. Now, okay, so now we are able to the proof. Okay, so now because P sub F of G, P sub F of G is positive, all right? So that the continuation probability of E given F under the probability function P sub F, which is PF G, and the PF, okay, E intersect G here. Right? So this is from the definition. Okay? From the definition. Okay. All right. And so that again, from the definition of the probability function P sub F, we know this is the probability of E intersect G given F, probability of G given F here. Okay? All right, and again, because probability of F is positive, so this conditional probability under probability function P is probability of E intersect G intersect F divided by probability of F. Okay. All right, and the denominator is probability of G intersect F, okay, divided by P of F. So we can cancel them. So this is becomes to probability of E intersect G intersect F. Okay? And this is the probability of G intersect F. All right. And so from the definition, we know this is the probability of E given G intersect F. Okay? All right. And so by using this probability function, P sub G intersect F, we know this is E, okay, from the definition. Okay, so this we have this one. All right, and similarly, so we can now we do this conditional probability under the probability function P sub G. Okay, so we can do the same procedure, and we find that we have actually PE given F intersect G. Okay, so this is P F intersect G of E. Okay, and so we have done. Okay, so we have that proposition. All right, so exercise. All right, so please discuss why proposition (3.5) is not true, right? When the joint probability of F and G is equal to 0. Okay. So proposition 3.5.b is true if this joint probability is positive. Okay. So when this joint probability is 0, then so I would say may not be true. Okay. Okay, and then an application of the previous proposition is here. If the probability of event F is positive, right? Then the conditional, okay, then the conditional probability, okay, of the joint event E and G given F is equal to PE given F, okay, times P E given G intersect F. Okay. And for event and for E1, E2, okay, up to En in the sigma algebra, probability of E1 intersect E2 intersect En given F is equal to probability of E1 given F, probability of E2 given E1 intersect F times probability of E3 given E1 intersect E2 intersect F times probability of En given E1 intersect E2 intersect intersect En minus 1 intersect F. Okay, so this is the this is actually multiplication rule, okay, given F, right. And you can compare with proposition 3.5.8 here. Okay, you can see. Right. When we write down the multiplication rules, there is no restriction to the event F. Okay, so the event F here, can have a positive probability or a negative or zero probability to occur. Okay, and so that and the reason is that we have shown P sub F is a probability function. Okay. But here we are expressing the conditioning under P, all right, under the original probability function. Okay, so the corresponding multiplication rule you can see here require that the probability that event F occurs is positive. Okay, we require this condition. Okay, so they are different between each other. Okay. All right. Right. So let me give a proof of this proposition. So if probability of G intersect F, okay, is positive, right? Then the proposition follows, okay, from proposition 3.5.A and 3.5.B. Okay? So first of all, we apply this one. Okay, we apply this one, and then because when this is positive, then we can turn what? Turn the the conditional probabilities under this piece of f probability function. Okay, to what? To conditional probabilities under the original function p. Right. So that is the. So this is the important thing that so we can turn this kind of conditional probabilities into conditional probability expressions under the original probability function. Okay. And which is just what we want. Okay. So now we consider the case that if probability of G intersect F is equal to 0, okay, then probability of E intersect G given F, okay? And by our definition, okay, got our definition here that this this is the ratio of P E intersect G intersect F. Okay. All right. So we look at the numerator here. You can see the numerator is the probability of the joint event of E and G and F. Okay. And as you can see, this intersection, this joint event, is a subset of this joint event. But the probability of this joint event is 0. So of course, because this probability is less than this probability already. But this probability is 0. So that means that this is 0 and PF. And remember, we assume P of F is positive, right? So that's why we can write down this expression here. Okay, so this is 0. Okay, so we know this is 0 here. Okay, this is 0. And we look at this probability P G of F. Okay, so Pg of F, all right, Pg of F is equal to Pg intersect F and P of F. And again, this is 0 and P of F, right? Because this probability is 0, and so this is 0. Okay, so we know this is 0, and this is 0. And this one, in this case, this probability is equal to probability of E, right? And probability of E may be positive, right? But it doesn't matter because this is 0 and this is 0. So 0 times anything is 0. Okay. So we have so we have so that probability of E intersect of G given F, which is 0, is equal to 0 times probability of E given G intersect F, and so this is probability of G given F times probability of E given G intersect F. Okay, so that so this gives us the case we have. Now, okay, now for a partition G1, G2, and Gn. Okay. Okay. My proof is just for this case. So maybe I will erase this part. And so exercise. All right, so please discuss please give a proper condition, or okay, maybe I okay. Now under what conditions we have okay, so we have conditional probability on E1, E2 up to En, and F. We have the following multiplication rule that En given F equal to probability of E1 given F, probability of E2 given E1 intersect F, that probability of E3 given E1 intersect E2 intersect F, that probability of En given E1 intersect E2 intersect intersect En minus 1 intersect F. Okay. Right, so this is an exercise. So under what conditions on that? Okay, and F. Okay, in the case here, okay, in the case here, right, the condition is that the probability of F is positive. All right, and so for two joint events here, okay, the conditional probability of this joint event of two events given F, okay, can have this kind of multiplication rule, okay, formula here. Now, if we extend the result to an event, okay, given f here. All right, and we would like to have this multiplication rule here. So what kind of conditions we need? Okay. Okay. So what kind of condition we need? Okay. You may start with this condition, right? Okay. You may start with this condition. Is this condition sufficient? All right, to guarantee this multiplication rule? If not, then what additional condition you should have? Okay, so that is for you to discuss. Okay, now, so basically you can see that in this section, okay, the conditional probabilities, okay, have the concept we introduced, okay, related concept we introduced in the previous sections. Okay, so actually you can see that we actually discuss all these concepts one by one, right? So one by one. So the next one is about, so given a partition, G1, G2, up to Gn of the sample space. S, okay. We have PFE. So that summation from 1 to n, and the PF GI intersect E. All right. So we have the following decomposition formula, right? Okay. Because P sub f is a probability function. Okay. And by applying proposition 3.5.8, okay, so we have PF of GI, P sub F of E given GI. All right? So this is a direct application of the decomposition formula for any probability function. Okay, for any probability function. But if we want to turn, turn probabilities, our condition probability under this probability function P sub f to be expressed under the original probability function P, okay, then we need proposition 3.5.b. Okay, so we need this one. All right. So and if probability of f is greater than 0, then in this case, okay, so in this case, now in this case, so we know that then this formula the probability of E given F, okay, is equal to summation I from 1 to n. And here, so this is a direct, we know from the definition GI given F. Now, but the problem is here, this one. Okay. So now, okay, so now we have okay, it's not only for this. This is becomes to PE given GI into sec F. Right. And the reason, okay, then let me write down the reason. Since, okay, all right, since that, because this one is just equal to this one, right? So, so you can see PF GI times PF E given GI. Actually, this is P of F GI intersect E. And the PF GI intersect E is equal to P E intersect GI given F. Okay. So that this is equal to probability of GI. Okay, so now P GI given F and times P of E given GI intersect F. Okay, this is from proposition 3.5.c. So this is by proposition 3.5.c. And to apply proposition 3.5.c, we need this condition. Okay, so that's why we need that the probability of F is positive. Okay. So that if probability of F is positive, then we have this decomposition formula. Okay, so it's again a version of decomposition. Formula. Okay? So it's a version. So it deals with this conditional probability. Okay? In terms of the original probability function P here. Okay? Because in our problems we need actually to compute the conditional probability of this one. Okay, so even though we can use P sub F, okay, P sub F to write down the decomposition formula, but to express this concept, this probability in terms of original probability functions, then you should impose extra conditions. So for here, we need that the probability of F is positive. Okay, and as you can see, because we need a proposition 3.5.c here. Okay. Okay. Now we discussed independence concept in a previous section in chapter 3, in this chapter. Okay. Now, we will introduce the concept of conditional independence. Okay. So now, we say that two events, E1 and E2, are conditionally independent. Okay, given an event F, if we use this probability function, all right, P sub F, to express, all right, to express the joint probability, which is equal to Pf of E1 times Pf of E2. Okay, and equivalently, this is saying that P conditional probability of the joint event E1 and E2 given F is equal to the conditional probability of E1 given F times the conditional probability of E2 given F. Okay. All right. There is no problem to write this probability in terms of the original probability function, okay? Because this is directly from the definition here, okay? Okay. I have to remind you that the difficulty actually is from the two-stage conditioning, okay? So with two-stage conditionings, there are some intriguing details that you have to be careful, okay? So that some additional requirement, all right, should be imposed before you can use these identities here. Okay. So that the two-stage conditioning, all right, can be right down to one-stage conditioning. Okay, one-stage conditioning. So that is very important, right? To turn a two-stage conditioning into one-stage conditioning. All right, and when you are given some additional properties. Okay, so this is about conditional independence between two events given an event F. Okay, so we have a proposition, okay, to connect the concept of a condition and a conditional independence with the two-stage conditional conditioning, like this one. Okay. So now, if E1 and E2, all right, are two conditionally independent events, okay, given event F, then we have this two-stage conditioning, okay, is equal to one-stage conditioning, okay, and the PF E1 given E2 is equal to PF of E1. Okay, so okay, because we have corresponding properties for P, right? And P sub F is a probability function, so that so we have that. And furthermore, okay, if that E1 intersect F, right, is positive, okay, then probability of E2 given E1 intersect F is equal to probability of E2 given F. Okay. Okay, so that is the way to turn the two-stage conditioning to one-stage conditioning. All right, so this is the corresponding to this one. Okay, corresponding to this one. But to turn the two-stage conditioning to this one, we require this one. This is from proposition, okay, 3.5.b. Okay, this is from. And similarly, and if probability of E2 intersect F is positive, then probability of E1 given E2 intersect F is probability of E1 given F. Okay, so this is corresponding to this identity here. Okay. Okay, so this one can be turned to this. All right, so we turn two-stage conditioning to one-stage conditioning. Right, and so require this property, and also we can return the two-stage conditioning to this one-stage conditioning. Okay. Okay. So now, so you can see how to prove this proposition. Okay. So now the first half. So the first half, right, of the statement follows from the definition of conditional independence, and a proposition in section 3.4. So and proposition 3.4.8. Okay? Because proposition 3.4.8 apply to any probability function. And P sub f, just a probability function we have shown. Okay, so this one, no problem. And so this is the first half. The second half is here. Okay, follows from, and the second half. So the second half follows from the first half and proposition 3.5 point B. Okay. So we need so we need proposition 3.5 point B. So we use proposition 3.5 point B. Okay. Okay. So we use proposition 3.5 point B to turn these two-stage conditioning into one-stage conditioning here, respectively. Okay. Now, proposition 3.5 point E, if either PF of E2 given E1, so if this two-stage conditioning is equal to this one-stage conditioning, or this two-stage condition equal to this one-stage conditioning, then E1 and E2 are two conditionally independent event given F. All right, and this is actually this directly follow from proposition 3.4 point, I think, B, yeah. Okay, so this proposition applies to any probability function. All right. Okay, so this discussion is about two conditionally independent events given F. Now we can extend to a finite number of events. The n events EI, I from 1 to n. Right. The n events are called conditionally independent given an event F if for selecting R indices okay, that the conditional probability of this joint event given F is equal to the product of the respective conditional probability. Okay, so equivalently, okay, we have probability of EI1 intersect EI2 intersect index EIR given F is equal to probability of EI1 given F times probability of EI2 given F. The probability of EIR given F. Okay. Okay, and as we discussed the unconditional independence before, now if EI, I from 1 to n, are conditionally independent given F, then each E sub j will be conditionally independent of any event formed by or formed from E sub I for O I not equal to j given F. Okay, so this is the same. All right. Now, an infinite set or we use an infinite collection of events is called conditionally independent okay, given an event F if every finite subcollection of those events is conditionally independent. Given F. And similar to these properties for finite number of events, then if E sub I, where I is an infinite index set. Okay, so we have an infinite collection of events. It's conditionally independent given an event F, then for any E sub j, so for any event in this collection, E sub j will be conditionally independent of any event formed from EI for all I not equal to j given F. Okay, so there are corresponding independent concept. Okay, when we consider conditional probabilities given an event F. Okay. So this is our definition, and the conditional independence is a new concept. Okay, it's a new concept. Just like independence among events. Okay. All right. And finally, corresponding to a sequence of independent trials we discussed in the previous section, we have a related concept here. So sometimes a random experiment, again, under consideration, right, involves in performing a sequence of sub-experiment. Okay, among others. Okay. And we usually consider the situation that the sub-experiment are called conditionally independent given an event F with probability F. So when the probability of an event F is positive, if given the event F, the outcome, so the outcomes of any group of sub-experiments have no effect on the outcomes of other other sub-experiment. Okay, so formally, if E sub I is an event whose occurrence is completely determined so it's completely determined by the outcome of the I sub experiment I from 1 to etc. Then E sub I is a collection of conditionally independent events given the event F. Okay, so this is about and if each sub-experiment has the same set of possible outcomes, then the sub-experiment and the sub-experiments are often called trials. Okay, they are often called trials. Thus, in many practical situation, we deal with we will deal with a sequence of conditionally independent trials, okay, given an event F. Okay, right. And so we may we have to establish a suitable probabilistic model XFP for such a sequence of conditionally independent trials given an event F. Okay. All right. So so this basically finished chapter number 3. Okay, so you have to study the textbook because there are quite a few good examples for you to practice the concept you learned in class lectures. Okay, and I hope that the additional concept and the propositions I mentioned in the class lecture will help you to understand the material of the textbook. Okay. So let's take a break of 5 minutes, and then we will start to discuss chapter number 4. All right. So the next lecture will be on chapter number 4 about random variables. Okay. So the first section, we will introduce the basic concept of random variables. All right. So when a random experiment is performed, we are mainly interested in some characteristics of the outcome right, instead of the outcome itself. And in many situations, this characteristic, all right, so these characteristics can be expressed as real numbers. For example, if the random experiments is to select students in this campus, okay, this NTHU campus. So we just select randomly, okay. And we are interested in some characteristics of that selected student. For example, the age of the student, okay, or maybe the height of the student, or maybe the weight of the students. Okay, so there are many characteristics to describe a student, right? So, this is the situation, and ages, weights, okay, they are all numerical values that can be, so they are real numbers. Even if we are interested in characteristics such as sex, maybe female or male, and you can actually represent these characteristics by numerical values. So you can set a 0 to female and 1 to male. Okay, so with this understandable mappings that you still can describe the sex of a student by numerical values again. All right, so that there are some descriptions about these characteristics. So this is a random experiment. And from the random experiment, you have an outcome, omega. So this you have an outcome, Okay? And with these outcomes, you will measure characteristics of the outcome. All right, so you may have a measurement device number 1. Okay, you may have a measurement device number 2, okay, etc. Okay, and you may have to measure device, say number n, so that that you use n measurement devices to obtain n characteristics, right? And each characteristic is expressed by real numbers. Okay, and so now we usually so the device will be named, say by x sub 1, all right? Device x sub 2, up to here x sub n. Okay. And after the measurement device, you have the x sub 1 omega, okay? And you have x sub 2 omega up to x sub n omega. Okay, so x sub 1 of omega, x sub 2 of omega, x sub n of omega, they are n characteristics of the outcome omega. Okay. And this, so in here, right, then x1, x2, up to xn are co-random variables. Okay. The reason why they are co-random variables is actually this characteristic, this number, this, because as we say, they are numerical numbers, and these numbers depends on the outcome. Okay, and as we know, the outcome appear, right, in probabilistic way. Okay, because that, as we have discussed that in chapter number 2, we have a probabilistic model for a random experiment, so that for each event of interest we select, we assign probability. Okay, that that event occurs, so that an outcome will appear in a probabilistic way, and so the corresponding characteristic values here will appear probabilistically or randomly, okay, and so that they call the random variables in the theory of probability. Now, we will give a formal definition of random variables. So you can see x1 represent measurement devices. And you can see that for each outcome, you have a value. Okay? So each outcome has a particular value. You cannot, for each outcome, through this measurement device, you cannot have two values, right? You should have one value. So this correspondence is actually a function. Okay? So mathematically, we use a function to describe, okay, a measurement device. Okay? And so with n measurement devices, we have n functions, x1, x2, up to xn. So random variables are functions. Okay, so it's very important that random variables are functions. Okay, so a real valued random variable all right, is a function from the sample space X, okay, from to the set R of all real numbers. Okay. So in this course, when we mention random variables, we will mean real valued random variable, except some other special cases. Okay. But they are just not functions. They should subject to a certain general property. Okay? And which will be discussed later. Okay? All right, so first key point is that random variables are functions from the sample space to the set of all real numbers. But second, that they are not just only functions. They should be subject to a certain general properties. Okay, and we will mention that later. Right. Okay, so there are some examples to mention. The first one is that in tossing a pair of dice, we may be mainly interested in the sum of the two dice. Okay? The sums of two dice. Now, tossing a pair of dice. This is a random experiment. Okay? And the sample space, well, the sample space consists of a pair of numbers. So it is it's ij. Okay. And ij, because that there are 6 spaces for each die, and and then the number appeared would be from 1 to 6. Okay, so the sample space is just the set of all pairs. Okay, so the size of X is 36 here. Okay, and the sigma algebra is said to be the power set of the sample space. Now, and the probability function, all right, X, the counting, okay, so it is the counting probability measure. Suppose we have a failed dice, okay, no cheating at all. So this is counting probability measure here. Now, when we interested in only the sum of the two dice, so let X from the sample space to R, okay, and for each joy, all right, so for each outcome, so outcome X a pair. Now the X of ij, all right, would be I plus j. Because we are interested in the sum of the two dice, so that would be I plus j here. Okay, so that X it's a random variable. Okay. So this is the functions here. And X is a random variable. Okay? As shown later. And the second example, in flipping all right, so, but we say that a random variable is a function subject to a certain general property. And we will see that since it satisfies the required general property. As we will see. Okay, so we will check that again back. And in flipping a coin n times, all right, so the random experiment is to flip a coin n times. We may be mainly interested in the number of heads that occur okay, so we're mainly interested in that. All right, and in this case, the sample space consists of n tuples. All right, so that is omega 1 to up to omega n, such that omega I is in either ahead or tail for I equal n. So the size of the sample space is 2 to the nth power. And the sigma algebra select will be the power set of x. All right, and the probability function is the counting probability measure. Okay, because we assume that the coin is a fair coin, so that you have equal probability to have either a head or a tail. Okay, so that's so this is the counting probability measure, and we let, but and for our purpose, we will use the omega I to be in 0 and 1. So 0 corresponding to tail, and 1 corresponding to head. Okay? Now, so we use this kind of model. Okay. So now x becomes to n-tuple, binary n-tuple, because the components are either 1 or 0, and 1 corresponding to h and 0 corresponding to tail. Okay, and so we establish a function, right? And so omega 1, omega 2 up to omega n goes to the summation of omega I. Okay. So the function value all right is the summation omega I. Okay, so you see that this sum is the number of heads that occur, right? Number of heads. So with this probabilistic model, so we have a representation of the sample space, and we can establish a function y, and the function value give you what? Give you the number of heads in flipping a coin n times. Okay, flipping a coin n times here. So you can see that, and we can see that this y is a random variable. Okay, since again it satisfies the required general property. As we will see. Okay. right. So recall that the smallest sigma algebra of subset of R containing all intervals in R, all right, is called the Fourier sigma algebra, okay, of subset of R. Okay, so and in R there are many types of intervals. Okay, so for example, so that they are so for okay, we have so for finite intervals with ending point A and B, we have, for example, open intervals, closed intervals, half open, half closed intervals. Okay, so actually we have 4 types of finite intervals. How about infinite intervals? All right, so we have like B, right? So we have B. Okay, so this is an infinite open interval, right? And this is an infinite, actually, closed interval, infinite closed interval here. Okay, so basically, you have 4 kinds of finite intervals, and you have 4 kinds of infinite intervals here. Okay, so they are all intervals to have. Okay, so all right, so because in many situations we want intervals to be so if the sample space, if the sample space is the set of all real numbers, then if intervals, all right, well, we like the interval to be events of interest. Okay, to be event of interest. And so, and any the smallest sigma algebra containing this kind of intervals, okay, will be called the Borel sigma algebras. Okay. Okay. Now, so that is the, and then now we talk about, so for a function, consider, so we next introduce the concept of the inverse of a function f, okay, of a function. All right, now, we know for a function, it may not have an inverse function, okay, except that this function is one-to-one and onto, okay. But we need a kind of concept of inverse of a function, okay, especially in the study of probabilities. Okay, so now we want to define such a concept, and we will see that this definition becomes to a very useful concept. All right, so consider, okay, consider a function f from a set A to a set B. So AB can be arbitrary set, okay, and for any subset so for any subset E of A we define f of A to be the set of all, oh, I'm sorry, f of E. So it's quite natural. So f of E is the set of all function values for all elements in the subset E. Okay? And in particular, okay, in particular, f of A is just the range. All right, so it's just a range, the range of of the function f, right? So f of A is just the range of f, because right. So this is f of x and x in A. Is the range. So it's the range of f, okay, particular. Now, and you can see that here, because f of x is in B, right? So that this set is actually a subset of B. Okay. is actually a subset of B here. Right. So for every subset of A, after the mapping of F, you have a subset of B. Okay, so that with a function f from A to B, we actually, so now we establish a function or a mapping, maybe I will use a mapping, or you can say a function, right? So mapping is another word of function from the power set of A to the power set of B. Okay? From the power set of B. Okay. And denoted as F, all right? So we use the same function F to describe. Okay, so this is actually from the power set of A to power set of B. And so E will be goes to F of E. Okay? As we describe here. Okay? All right, so originally, this function F is a point function because that assign each element in A, you have a value in B, right? So that here. But in here is that for each subset of A, you have a corresponding subset of B. And the corresponding property of B consists of all values, all right, obtained from all the elements in E, okay, from here, this definition. Okay, so now, so this has become to a set function, okay? So this has become to a set function. So from a set to a set of, right? All right, so this is that. Now we define, now for, so with the similar argument, so for any subset, okay? For any subset G of the codomain, B of F. All right, so we define the inverse of F, okay, to be what? To be the all element in A such that F of X is in G. Okay, so the inverse mapping is here. So this is B, this is A, okay, F here. Now if we select a subset G here, so now we will, so the inverse of G would be all the okay, so they all goes to there. Okay. All right, so from here, we know this is a subset of A. Okay. So inverse of G, because G is a subset of the codomain B. Okay. All right, and so this is the definition. Okay. definition here. All right, so the inverse of G gives us a subset of the domain such that all element in this subset has function value in G. Okay, so you see it's function value in G here. Okay. Now, so in particular, so we have the inverse mapping of the codomain is just the domain A. Okay, the domain A here. And then we establish a mapping or a function from the power set of B to the power set of A. Okay, and denoted as F inverse. Okay, so F inverse is from the power set of B to the power set of A. All right, the power set of the codomain to the power set of the domain. And for each G, for each subset of B, you get the inverse mapping of this G, yeah, defined here. Okay. So this definition of inverse mapping gives us a very useful concept, because that you always have such a inverse mapping for any function here. Right? No matter it is one-to-one, or no matter it is whether it is one-to-one or whether it is onto arbitrary function. For arbitrary function, you have this and this one, right? You have this. All right, then I will list some properties of the inverse mapping. Okay, here. Okay, so they are very useful. Okay, so for proposition 4.1.A. Okay, so let F be a function from a set A to a set B. Okay. Okay. And then let GI be a collection of subset of the codomain B and G a subset of B. Then we have the following properties. First of all, if we take the inverse, okay, of G complement, then this is equal to the complement of the inverse of G. Okay? Second, the union of all GI in this collection, okay? And then you take the inverse mapping, then this is equal to the union, okay, of the inverse of each EGI. Third, when you take the intersection of all GI in this collection, then this will come to intersection of all the inverse of GI. So which shows that the inverse mapping is commutable with the complement, commutable with the union, and commutable with the intersection. Okay, so you can exchange the operations. Okay, so inverse mapping is very, very, very nice from these three properties here. Okay, so you can see that. And to show a proof, okay, you can see here. So let me write the proof here. Okay, for the one here. Let's see. To show two sets are equal, we can show that they have the same elements. All right. So if X is in the inverse mapping of the G complement, okay. So if X is in here, then which means that f of X is in G complement. Okay, so f of X is in G complement, right? It's in G complement. So that so this if and only if f of X is not in G here. Okay, so f of X is not in G. When f of X is not in G, so that means that X is not in the inverse of G. Okay. And which says that X is in the complement of this subset. Okay, so if X is in this set, then X is in that set, so that these two sets are the same. Okay, these two sets are the same. Second, X is in the inverse mapping of this union. Okay, which means that f of X is in the union of GI, which means that all right, which means that f of X is in GI, okay, for some I in I in the index set. So, which means that X is in the inverse mapping of Gi for some I in the index set. Okay, and so which says that X is in the union I from 1 I in I of inverse of Gi. Okay. All right. So we show that these two sets are equal. And third one, X intersection. So X is in the inverse mapping of the intersection. So which says that f of X is in the intersection of Gi. So which says that f of X is in Gi for all I in index I. So this is saying that X is in the inverse mapping of Gi for all I in the index A. And so X is in the intersection of the inverse of Gi. Okay. All right. And so we have done. Okay. All right. So inverse mapping is very beautiful that you have that properties here. Okay. Now, so now we will describe the so we will describe what is the general properties. Okay, what is the general properties there? All right, so now I will give a precise definition of a random variable. So a real valued random variable. Okay? A real value random variable called X, right? on the sum space. All right. So okay, a random variable X on the sum space X is a function from X to the set of all R such that x inverse of B, okay, x an event of interest in F for all B in the Fourier sigma algebra. Oh, all right. We will call, okay, the Fourier sigma algebra denote as B, okay? So we use B to denote the Fourier sigma algebra of a subset of the set of all real numbers. And, oh, okay. And, all right. And a member B in the Fourier sigma algebra will be called a Fourier set, right, in R. Okay. I forgot to mention that. So in particular, these 8 kind of intervals are Fourier set in R. Okay, so they are Fourier subset of R. Okay, because we intended to include these intervals in the member of the Fourier sigma algebra. So that these intervals are Fourier set. And of course, that by using complement, countable many union, or countable many intersections, you can, on these intervals, you can obtain uncountable many Fourier subset. Okay, so Fourier subset are versatile. Okay, they actually have many different characteristics. Okay, all right. So they are called, and so the general property. So this is the general property. The general property is required for any random variables. Okay, so a random variable actually is a function from the sum space to the set of all real numbers when we consider real value, the random variables. And satisfying this property means that the inverse mapping of a Fourier set. So B here, because B for all B for all Fourier set B in the Fourier sigma algebra B on R. Okay? So maybe I will up to here. And I will explain why we need such property, general property. Okay, first of all, we see mathematically, right? Because x is a function, right? So it's x equal to r here. Now, and so we know from that we can have a mapping from the power set of the sum of space to the power set of the set of real numbers. Okay, but this one, as we know, this one, all right, accepted directly from this function. But we also define the inverse mapping, which is very interesting. So this is from, okay? So that it is from the power set of R to the power set of X. But as we know that in probability theory, that these two, in general, these two is too big, right? And in many situations, this is also very big, except when X is a finite state, or when X is a countably infinite state. Okay, but in general, this is very complicated. Right, and so that what we want is that if we restrict, so we have this general inverse mapping. But the Fourier set, the Fourier sigma algebra, the B here, script B, is a subcollection of the power set. Okay, so the requirement, okay, so we require that when we restrict the inverse mapping to the Fourier set, okay, because so this is the restriction. Okay, so let me use that restriction. Okay, because B, notice that it's a cup collection of 2 to the r. Okay, because 2 to the r, the power set of all, the power set of r is the collection of all subset of r. Okay, and the Fourier sigma algebra is just a subcollection, okay, of this one. Okay, so this is very huge, all right, but so that is very hard to deal with this power set. And in probability theory, we deal with only the Fourier sigma algebra here. Okay, so now we require that when this inverse mapping restricts to B, right, restricts to B, then that the B can becomes to a mapping, all right, to what? To F. Okay, to F. So every Fourier set up to the inverse mapping, so every Fourier set up to the inverse mapping will give you an event of interest in F. All right. Right. So mathematically, right, this is the requirement. Because that if this is an arbitrary function, all right, even though we know the inverse mapping is from the power set of R to the power set of X. But it is possible that if a Fourier set here, after the inverse mapping, will not be an event of interest. Okay? Maybe it's just a subset of X, but may not be in here. Okay. So this is the requirement, all right? This is requirement. And the reason is here. So this is the required general property. Okay. The reason why we need this, we require this general property. The reason is that we usually use random variables to describe event. All right, to describe events. All right, so we usually use random variables to describe events in the following way. All right, so that so let I be an interval of R. Okay, so I can be one of these A types of intervals. Okay, so I be an interval of R. Okay. An event that a random variable x is observed. Okay. Is that the observed value of a random variable x on the sample space x in I. So an event that the observed value of a random variable x on the sample space in I, i.e. x, all right, of omega. So that the event E is that the value, all right? So because omega is the outcome of our random experiment, and the observed value of a random variable, which is just x of omega, right? So the observed value is in I. Okay, and so this one describes a subset of x. And we want this event E to be an event of interest. Why? Because an event of interest, we can assign probability only to event of interest. Because all the event of interest has been included in the selective sigma algebra. And the probability function is defined only on the sigma algebra F. Okay? So only event of interest can be assigned a probability. Right? So if an event is not of interest, it means that if E is not in the sigma algebra script F, then we cannot assign probability. Right? And then this is not what we want, right? So an event E that the observed value of a random variable x is in I, okay? All right, so this is the description, right? Right. So be an event of interest, i.e. E should be in F, right? So that we are able to assign a probability P of E to this event E. Okay, since P is a function with domain F. Okay, domain F. Okay, so because interval, right? So the value, for example, if the running experiment is to randomly select a student from NTHU campus, and the X is the weight of the student. Now, so we want that the weight of a student is in between 50 kilometers to 100 kilometers. Okay, so 50 kilometers to 100 kilometers is an interval. Okay, it's an interval. Okay. And we want to know the probability that an NTHU student, right, has weight in between 50 kilometers and 100 kilometers. Okay, so we want the probability of this event. All right, so this is usually, we want such event to be an event of interest. Okay, and what is this event? Okay, you can see, what is that? What is that? This is exactly the definition of inverse mapping. Okay, the definition of inverse mapping of I. Okay, the inverse of I. So for every interval, okay, so for every interval, the inverse mapping, okay, so we require that so maybe so we require, okay. That for every interval, the inverse mapping of the interval, okay, the E should be in F. Okay. Okay, and then now I think all right. Okay. So that okay. All right, so that's we require that X X inverse of I is in F for any interval I of R. Okay. Now each Fourier set be in the Fourier sigma algebra, it's obtained by countably many complements many operations of complement union our intersection. Okay? Because the Fourier sigma set is the small sigma algebra containing all intervals. So they can be obtained for that. All right? And by proposition 4.1.8, okay. If we do complement, right, in the codomain. So here, if we do complement, right, in the Fourier set, in the Fourier sigma algebra here, then when we do the inverse mapping, it's just like to do the complement, right, of an event here. Okay, so by propositions 4.1a that X inverse B, right, is contained, okay, it's a member, okay, it's a member in the smallest sigma algebra, okay, containing all x minus I, okay, or containing the inverse mapping of I for all interval of R. Okay? So that X inverse B, okay, must be a member of the sigma algebra F. Okay? So, so the reason that why we need this required general property is because that we need such an event to be an event of interest. Okay, and in many contexts, we describe this event as by saying that we use this statement, mathematical statement, say that random variable is in I. Okay, even though this is a little bit misleading. Why? Because x is a function, right? So, but in the literature of probability theory, that mathematicians use this notation. Okay, so that it is quite often that you will see that, and also in my lectures that I will use this mathematical description, this phrase, to describe this inverse mapping. And actually, this is an event. So that so actually, X belongs to I means that it's the set, is a subset of all. Is the set of all outcome, such that the value X of the corresponding value under the mapping X is in I. Okay, so a precise interpretation of this, okay, of this expression is here. Okay, so this is a very important expression, okay, to this one. Sometimes you can write it by use the inverse mapping. Okay. Okay. All right. So that so this is the general property required. Okay, and so now from the previous discussion, we have the second proposition. Okay, a function x, okay, from the sample space to the set of all real number, all right, it's a random variable. Okay, so a function is a random variable if and only if the inverse mapping of I is in F for all interval I in R. Okay, so it's easy to verify whether a function, a real value function on the sample space, to be a random variable. Okay, if we can check that for every interval, okay, in R. Okay, so that is a good thing to see, and now a special case. When a very special case is that when the sigma algebra is the power set of the so if the sigma algebra is the power set of the sample space, then any function x from the sample space to R is a random variable. Since x equals I is a subset of x, right? The inverse must be a subset, and right, and it's in the power set of x. Okay. Okay. So this is quite often that if we have a finite sample space, we usually take sigma algebra to be the power set of x. And in this situation, then any function on the sample space is a random variable. Okay, it's a random variable. So this gives us many examples, right? So we don't need to check here because the sigma algebra select is the power set of x. Okay. So from here you see, if you select a sigma algebra which is too small, all right, which is too small, then so for example, if f is a proper subset of this power set, then a function on x may not be a random variable. Okay, may not be because that this one, this is a subset, of course, but this one may not be in F in the sigma algebra you select. All right. Okay. So for our, this is the reason why when X is a finite sample space, we select the sigma algebra as the power set. Okay, it's a power set because that any function on X would become to a random variable. All right, and we can describe events by using various random variables. Okay, so that is the idea we have. Okay. And Now, for our further discussion, okay, for a random variable, okay. So random variable is just a abbreviation of random variables, okay. X, the function defined by, so f of x is defined to be the probability of the relation here. So x is less than or equal to x. So what is that? X less than or equal to x is actually just like this one. Okay, it's an event. So x less than or equal to x. What is that meaning? Means that x is in this interval. Okay, it's in this interval. So it is the event such that okay, and also okay. So a good interpretation is here. The event x, random value x less than or equal to x means that its value, okay, is then x. So it is the subset of x consisting of all outcomes such that the value under x of these outcomes is less than or equal to little x. Okay. All right, and as we know, this is the inverse mapping of an interval. Okay, so it must be in the sigma algebra because x is a random variable. Okay, so we have this one, and so we can assign probability, right, to this event. Okay, so this is actually probability of inverse mapping. Okay, so that px less than the capital X, the random variable. So this function, okay, has a value less than less than x, and this event is actually this event. Okay. Right, and this function, and we define for all x in R. Okay, so for every x in R, we have a function. So this function is called the cumulative distribution function. All right, so called CDF of the random variable x. Okay. And you have two simple properties. Okay, of a distribution function. First of all, distribution function has value in between 0 and 1. Second, if A is less than or equal to B, then FA is less than or equal to FB. the first property follows from the property of probability functions, because that for any event, its probability will be between 0 and 1. Okay? And f of x is just the probability of certain events. So of course, this is true. And the monotone increasing property here says that f is monotone increasing, right? So that so a proof is here. Okay, we prove this one. If A less than equal to B, then the then the event x less than equal to x A, which is equal to the omega, such as x of omega less than equal to A. Okay. And this one is contained in x less than equal to B, because this is the set of. So any omega such that x of omega less than A must be less than B, because B is bigger, right? Okay, so this event is bigger than this event. Okay, and so that and then by proposition 2.4.1, I think that the probability of x less than A will be less than probability of x less than B here. Okay, by proposition, I think it's 2.4.1. Okay, and this is f of, by definition, f of A, and this is by definition is f of B. Okay, so we have this one. So we have these two properties. Okay, for any CDF. Okay, for any CDF of a random variable. Okay. Okay. Now, in the second section, we will consider a special type of random variable called discrete random variables. All right, random variables x that can take on one of at most a countable number of possible values is called discrete. Okay, so x take, and that is x is a discrete random variable, if and only if the event is the empty set for all x in R except a countable number accountably many number of possible, maybe I just say accountable number of possible x. Okay? So it can only, for example, the value can be any integer, or can be any non-negative integer. Okay, so they are called, or the value can be any value between from 1 at the integer values 1, 2, 3, 4 up to n. Okay, so that they are all discrete. Okay, and so for a discrete, random variable x, we define the probability mass function called PMF. Right. So P of x is defined to be the probability of x equal to little x. Okay, for all x in R. So this is the probability mass function. Okay. So the event is that x equal to x, right? Exactly. So this is what is that? Okay. So this is the probability that inverse mapping of the singleton. Okay. Okay. Or probability of omega such that x of x equal to x. Here. Okay, so little p, this is called the probability mass function. Okay. So it is clear that one, the probability mass function has value in between 0 and 1, because that this is an event, okay, and the probability of an event must be in between 0 and 1. The second, P of x is equal to 0 for almost all values of x in R, except a countable number of possible x. Okay, so that this is the two property of probability mass function. Okay. Now if a sub I and I in an index say are possible values of a discrete random value x, where because x is discrete, so it can take only at most countable many values, so that the index say I. So the index say I is a countable index say. Okay. Then the event x equal to a sub I, all right, omega in S, such as x omega equal to ai for all I in I, so this are the most basic event which can be described by discrete random variable x. Okay, so this is the most basic event. And as we can see that we have two properties. First, this event is a partition, okay, of the sample space. Okay. All right. They are disjoint, of course, and their union is equal to the sample space. Okay, because that a sub i's are all possible values, so that this is become to a partition of the sample space x. And the second is that the summation of x in I, okay, the index say I in I, and the p of ai, which is equal to summation I in I, and p of x equal to ai, which is equal to 1. Okay, which is equal to 1. Okay, so we define in here, up to here, okay, we deal with discrete random variables. Now a question. All right? X, a function x from the sample space to the set of real number, which takes, right? So which takes on one of at the most accountably or accountable number of possible values. Okay? Right, so if we look at a function, just a function, okay? And we know that this function takes on one of at most a countable number of possible values. Is a function a discrete? Is a random variable? Okay, so we have this question. Okay, and so an exercise. Please show that the answer is yes. Okay, so so we don't need to check the required general property. Okay, in this case. Okay, whenever a function from a sample space to the set of real number, and we know its range is a countable set, right? So which takes on one of at most a countable number of values. So this phrase, which take on of one of the most countable number of possible value, is the same to say that it's a countable set. So, which means the range of X is a countable set. Okay? Just like here, if we, the same, right? Take on, this is saying that the range X of the function is a countable set. So if we consider a function, then whose range is a countable set, then that this function must be a random variable. Okay, so this is an exercise to ask you to show that the answer is yes. Okay, and so it gives you very convenient insight to see that to justify a function to be a random variable, you can investigate and find that this function has range which is countable. Then this function becomes to a discrete random variable. So it is a random variable, and and it's also a discrete random variable. Okay, discrete random variable. And for a discrete random variable, we can use probability mass function to describe it. Okay, to describe it. Okay. And we find that the possible values here, okay, you will use the possible values A sub I to form a countable partition, okay, countable partition, and we find that this sum is equal to 1. Okay. So the study of discrete random variable becomes to be easy, okay, depends to be easy. All right, now the CDF we defined before, f of x. So the cumulative distribution function of a discrete random variable x can be expressed by its probability mass function p of x as follows. Okay. The f of x, okay, so that this is we know this is the probability that that x less than equal to x here. Okay, and so that this is becomes to the probability that union of AI less than x and x equal to AI, and this is disjoint. Okay, because A sub I are possible values, so that we want the function value to be less than or equal to x. So we should include all function values to be equal to AI, such as AI is less than or equal to x. And as we know, x equal to AI form a partition. Okay, so they form a partition before. Okay. So this has become to a disjoint union here. And so that this becomes to AI less than or equal to x, probability of x equal to AI, but this is equal to AI less than x, P of AI. Okay, so you can see the CDF, the cumulative distribution function of a discrete random variable, can be obtained by its probability mass function, little p of AI. And AI is less than or equal to x. Okay, so this sum is the countable sum here. Okay, all right. So so I stop here, and so I finished the first two sections of chapter 4. Okay, and we will continue the discussion of chapter 4 next Tuesday.